I said it was like this.
All right. Are there any questions?
Are we gonna be able to retake the test that we just did? Is that when we're able to retake?
No. No.
Okay.
Now, the way that I do the grading for that is how well you do in comparison to either this class or all the 1/10ths that I've ever had take that test. So that way, if I have a crappy semester, and then you're not penalized for it, or if this is an awesome class, you're not penalized by that either. So if I'm having a crappy semester, then most likely you'll be compared to people in the room. If you are an awesome class, you'll most likely be compared to the less awesome classes in the past. I don't know. It does not look like it made you feel any better. I guess we'll find out.
Do we have test corrections?
No test corrections on this one.
Can I ask a question from there since everybody did it already?
Okay.
How did rocket fly?
How do rockets fly?
From question from test, like
Oh.
because I thought it was like on constant speed first and then accelerating after it, but
So,
I don't know.
This is the rocket that's moving off to the right.
Like I thought it will be like this first, like at constant speed, and then after it drop part, it will be
All
like
right.
curve and speeding up.
And then for improvement, for a couple people, class this size, probably 3 most improved will get a bonus quiz grade. All right. So let's talk about thermodynamics.
What you're saying is I should have intentionally sabotaged the first attempt so that I could improve.
Sorry, I missed that, Ty.
So then what you're saying is I should have intentionally sabotaged my first attempt. So
There's been some people who have actually tried to do that, but for the students that I've had more than one semester, such as, it never seems to come across like they deliberately sabotage themselves. All right, so we last left off with energy conservation. I know it's a strange and wonderful concept. I'm pretty sure I did hit play. Or record. Yeah. Oh, I didn't tell it to focus on anything in particular. Let's get a focus right there. So, if I have my container of water, and I drop a hot piece of metal into it, and as you can see right here, we have our hot pieces of metal, and there's water in the cup. Then whatever energy that the metal loses will be gained by the water, and we can predict what that final temperature is going to be. Now, room temperature seems to keep changing. It's now 21.7 degrees Celsius. So we'll work through a problem with just some different numbers, and then we'll actually apply it to what we have here. And there's sometimes a concern when you put the water on and you start boiling it, that if the water runs out, well, one, you can do damage to the Pyrex, but also the blocks will be partly exposed to the air, but we are not in danger of that, so we will not worry about that part. So the change in energy of the water plus the change in energy of the metal is equal to 0. We are making the assumption, though, that there's no energy lost to the environment and to the air, because this is all surrounded by air here, and this is one of the reasons we use the styrofoam cup. And one of the things we're going to do in order to try to keep the energy contained is we have the top part to it, which we'll put over it, and then we'll poke a hole in this in order to get the thermometer into it, or a temperature probe. So let's say that I have 100 grams of water, and this is 50 grams. And specific heat of water, 1 gram. Try that one again. 1 calorie per gram degrees Celsius. And specific heat of the metal will make let's make 0.3 calories per gram degrees Celsius. Now, when there's energy exchange because of temperature difference, which is what we have right here, we're talking about heat. So this is the Q of the water plus Q of the metal equals 0. Well, if you flash back to your notes from 2 days ago, what's the formula for Q?
MC change in T.
Yes. It almost rhymes. It's C change in T. So this is mass of the water, specific heat of the water, change in temperature of the water. I'm just going ahead and bring this over to the other side. Equals negative mass of the metal, specific heat of the metal, change in temperature of the metal. Now, with that negative sign is going to be taken care of because one of those temperatures is going to be positive. Oh, sorry, one of the changing temperatures will be positive. The other one's going to be negative. So, I have 100 grams of water. Apparently, I did not click that well enough. I have 100 grams of water times the specific heat of water. Times the change in temperature. I don't know what the final temperature is. That's what we're trying to find. That's my unknown. So, but this is going to be T final minus the initial temperature, which I did not present here. So let's go ahead and do that. Let's put the initial temperature here of the water. It'd be 20 degrees Celsius. And the initial temperature here of the block of the metal will make 80 degrees Celsius. So the water, it's final minus initial, so it's T minus 20 degrees Celsius. And that's going to be equal to the negative of the mass of the block there, which is 50 grams, times the specific heat of it, which is 0.3 calories per gram degree Celsius, times the temperature, which is the final minus the initial, which is 8. So let's, so first, any questions before I just present this as a math problem and then we work through the math? Then let's present the math. All right, so I'm basically going to take that, except I can do some of that multiplication. 100 times 1, I got that one. So I have 100 times T minus 20 is equal to, then I have 50 times 0.3, negative 15 times T minus 80. 50 times 0.3 is 15. The negative, because there's negative over there. It is now a math problem. How do we solve this? What would be the first step?
Distribute.
Okay. So I got a binomial with a number out front, so we just multiply it through, so I have 100t minus 2,000 equals negative 15t plus 600? No, that's not right. 800, 400, 1,200.
Oh, that's a plus 3.
Oh, over there is
I thought it was negative 3.
Oh, no, no, no.
Yeah, I'm confused. You put your negative out. Okay, I see, sorry. Okay. Yeah, okay, sorry. I'm sorry.
Is it 1,200?
Yeah.
Okay, thank you. Now what?
You could, put your combined like terms on the same side.
Okay, so I guess I've got t's over on the left. So we'll add 15t to both sides, plus 15t. We'll get the constant over there, so we'll add 2,000 and plus 2,000. So I got 115t is equal to 3,200. Now what?
Divide by 150.
So t is equal to 3,200 over 115. Now before we actually come up with that final answer, this is similar to a problem we discussed last time. I know that the iron block has a much lower specific heat, or specific heat capacity also works. It has a lower specific heat, so it's going to give up energy much faster than the water will, which has a much higher level, which is fortunate for the Earth. So if they were the same mass, I would expect the final temperature to be much closer to 20 than it is to 80, just because the iron, again, the metal is going to give up much more. But it's also less mass. So, but considering that this is more than 3 times that, but the mass is only twice that, I'm still expecting the final answer to be closer to 20 degrees Celsius than it is to 80 degrees Celsius. And now,
27.82, 60, 87 degrees Celsius.
thank you very much. And there we go. That is the prediction. Needs to be a trend here. All right, so now let's figure out what the temperature of this water is. It should be somewhere around 100 degrees Celsius, just a little bit less than, because once the water hits roughly 100 degrees Celsius, it's going to boil up, so it's generally just shy of that. Let it settle down. So that's, we'll go with that as the initial temperature of the water, and, ooh, actually, we should not make that assumption. It's still creeping up. We're almost at 96 degrees. Oop, and back down again. All right, and the initial temperature of the block, 95.5 degrees Celsius. Well, I just messed with that, so that's going to change this. All right, I'll let it settle again. All right, so while we're waiting for that to settle down, let's take a look at the 2 metal blocks. I have 2 metal blocks in there. One I'm pretty sure is aluminum, and the other one I'm pretty sure is iron. So I measured the dimensions of the aluminum. So first off, let's do some confirmation. I'm about to erase this. Anybody need any of it? All right, so the volume of the aluminum. It's a rectangular solid, box shape. I gave the dimensions over there, 31.8 millimeters by 31.8 millimeters by 32.40 millimeters. I got that level of precision because I was using a vernier caliper. That's one of these things, and this measures down to the precision of a 1/2 millimeter. Sorry, a 1/20th of a millimeter. So how do you, if it's basically a rectangular solid, how do you find the volume?
That's right.
Yep. So 31.80 millimeters times 31.80 millimeters times 32.40 millimeters. What do we get?
$32,764.176
32,764
millimeters cubed.
There we go. There's a group got it. Millimeters cubed. Now traditionally, we're either want in cubic meters or cubic centimeters. Let's go cubic centimeters. How many decimal places do I move it over to go from cubic millimeters to cubic centimeters? How about millimeters to centimeters? How many decimal places?
10 or 10, 1.
Okay, 1 decimal place. How many
So-
convert?
So 3.
Yes. I have to convert all 3 millimeters into centimeters, so I'm going to move it over 1 space for each one. So 1, 2, 3, and it's 32.76417 cubic centimeters, or cc's, or milliliters. The mass of the aluminum, I first found an offset. It wasn't much of an offset, but I found the offset of 0.02 grams. So that's why I subtract 0.02 grams for my mass measurements. Oh,
Would
yes.
it be 1/8 because you're rounding? The 6, the 7, and the 6?
Oh, 32.8.
32.76418.
Oh, 1/8. Okay. Oh, I stopped short. That was the problem. Yes, you were right. Yeah, I don't know why I didn't keep going. All right, so the mass of the aluminum, the block itself was 89.69 grams. Subtract the offset because it was just slightly off to begin with, and I get 89.67 grams. So the mass, so my density, which is mass divided by volume, is that number I just said, 89.67 grams over 32.764176 or 8 or wherever you want to go, cubic centimeters.
Um, 2.736830282 grams per centimeter cubed.
Yep. Now I looked up the density of aluminum. Now this is not pure aluminum. I had a student who gave me a sample of pure aluminum, and over the course of several years, it slowly oxidized and turned into dust. I now have what remains in a Ziploc bag. However, it's not pure aluminum. However, the accepted value for the density is 2.7 grams per cubic centimeter, and we got 2.74. So pretty darn close to the accepted value. I'm pleased with that. Questions before we confirm that the other one is iron? All right, so let's go through and iron. Will be in purple. Fe for the chemical symbol for iron is 31.80 millimeters by 31.70 millimeters by 31.75 millimeters.
$32,005.005. 0.905. millimeters cubed.
And in centimeters cubed,
Three places.
32.005991
oh, you want to take it that far? Okay.
to make it even with the last one.
All right, cubic centimeters. So the density is the mass, and I went through the same process. The mass of the iron is 248.78 grams after subtracting the offset. So 248.78, so 248.78 grams divided by 32.00591 or 05 cubic centimeters.
$7.7729